Sometimes when we're observing some kind of phenomenon in nature, we're interested in finding a function, but what we can see from data really is information about the derivatives of that function. So we end up with an equation in the derivatives of a function that we're looking for. And that equation in derivatives is called the differential equation. And knowing the derivatives means that we can usually figure out what the function of interest is with a little bit of integration. So a differential equation let's say in x and y is an equation involving x, y, and derivatives of y. Could be first derivative, second derivative. Let's say we go up to the kth derivative. I'll put k in parentheses to mean kth derivative. If the highest derivative we see is the kth derivative, we call it a kth order differential equation. So let me put up an example. So a second order example might be something like y double prime plus 2xy prime minus 6y equals e to the x. So we can see in this equation we have x's, we have y prime, we have y double prime. Another second order example is 3y double prime plus 5y y prime equals x. So these derivatives and x can appear anywhere in the equation. A first order example is y prime equals 2y. In this example we can't even see x, but that's okay. We don't absolutely have to see x. We don't absolutely have to see all the derivatives either. We might just have the kth derivative in x, or the kth derivative in y, or some collection of these things. We don't have to see all of them. So here's a first order differential equation in which we can see y prime and y, but we can't see x. So this differential equation tells us something about how the function we're interested in is related to its derivatives and to x. And we're interested in what that function is. And we say that we've solved a differential equation if we found out what the function is, y in this case. So a solution of a differential equation in x and y is an equation in x and y with no derivatives appearing. Such that if we solve for y and y prime and it's all derivatives, those formulas satisfy the differential equation. So that if we solve for y, let's say y equals some function of x, y prime then is going to be the derivative of that function then these satisfy the differential equation. So, for example, let's take the first order differential equation I put up before. Y prime equals 2y as solutions. I found that y equals e to the 2x is one solution. Y equals e to the negative 2x is another solution. There's even more than that, but let's look at these. So if y equals e to the 2x, then y prime is 2e to the 2x. And our differential equation says y prime equals 2y. So we have y prime here, 2e to the 2x, and 2y is 2e to the 2x. So yes, they're equal. So this function and its derivative satisfy this differential equation, y prime equals 2y. So we say that they're solutions. we say that y equals 2x is a solution. So let's verify that y equals negative 2x is another solution. So if y equals negative e to the 2x, then y prime is negative 2 e to the 2x, and y prime is negative 2 e to the 2x, and 2y is 2 times negative e to the 2x, so negative 2 e to the 2x. Yep, those are the same. So y equals negative e to the 2x is another solution of the differential equation y prime equals 2y. Now typically there's infinitely many solutions to a differential equation.